Alright, so this is the Honors Chemistry lesson video for section 6.3, and this is going to be part 1 because there's quite a few periodic trends we got to cover, so I'm going to cut the video into 2 different parts. So periodic trends are trends that occur as you move down or across the periodic table. Now, as with every trend, like a clothing trend, even though a lot of people might be wearing it, it doesn't mean everybody's wearing it. Periodic trends happen the same way. A lot of elements follow the trends, but there's always going to be some exceptions. And so we'll talk about why some of those happen too. So the first thing we have to talk about is called effective nuclear charge, and it will be represented by Z sub EFF. So Z effective or effective nuclear charge. Since electrons are negatively charged, they are attracted to nuclei, which are positively charged, because of course opposites attract and like repel. Many of the properties of atoms depend on their electron configurations and how strongly their outer electrons are attracted to the nucleus. So when we're going over all of these trends, make sure you're focusing on how much the nucleus would be pulling on those electrons, and that's the basis of our effective nuclear charge. So the force of attraction between an electron and the nucleus is based on Coulomb's law and depends on 2 amounts. The first amount is the magnitude of the net nuclear charge acting on the electron. So in other words, how positive is the nucleus? And then the second thing it's based on is the average distance between the nucleus and the electron. So it doesn't matter what class you take, when you're focusing on attractions and repulsions of different forces, it's always based on the amount of charge and the distance between the charges. And that's what Coulomb's law is based on, and that's what we're going to focus on right now. How positive is the nucleus, and then how close are the electrons to that nucleus. So effective nuclear charge is the actual nuclear charge minus the shielding of the core electrons. So Z effective is always less than actual nuclear charge. So Z effective is just your actual nuclear charge, which the way you get that is using the atomic number, minus the screening constant, which is the number of core electrons. The thing is, the further out the electrons are, the more core electrons that kind of block the nucleus from the valence electrons. Okay, so think of it as it just blocking some of that positive charge. And so that's what your screening constant is. So your screening constant is your number of core electrons. So those are not the valence electrons, which sometimes is very easy to figure out, but when you get past that D sublevel, and we'll look at one like that, it might be a little trickier. So it says calculate the Z effective for argon and for krypton. Okay, so Z effective is just our actual nuclear charge minus the screening constant of those core electrons. So if you look at argon on the periodic table, the atomic number is 18. Alright, so you may need to get a periodic table out, not only for this video, but possibly for part 2, because having a periodic table while you're watching this is very helpful. Because see, I'm looking at the one on my wall, but you can't see that right now. Alright, so argon has a nuclear charge of 18. And when I look at it, it has 8 valence electrons, because it's in group 18. So it also has 18 electrons total. So if I take away just the valence, that means there are 10 core electrons. Okay, so remember, for a neutral atom, the number of protons equals the number of electrons. So once I determine there are 18 protons, I know there's 18 electrons total. Since it's in group 18, 8 of those are valence electrons. So 10 of them are core electrons. Like you just subtract the valence electrons. So once I subtract that, I get 8. So my Z effective or effective nuclear charge for argon is 8. So next I'm going to do it for krypton. So again, Z effective is Z minus S. So krypton has an atomic number of 36. Now a lot of people, they then want to subtract only 18 electrons from it because of the fact that that's all the previous rows, but D sublevel electrons do not count as valence electrons because the D sublevel is always 1 energy level behind. So like when you fill in 4s, then you go back to 3D. So those are not valence electrons. Those are core electrons. All right, so we know that argon is in group 18, so 8 of these are valence electrons. So that means the rest of them are core electrons. So that means 28 of them are core electrons, not just 18. Because that D sublevel, those 10 are also core electrons. So once I do 36 minus 28, I get 8 again. So both argon and krypton have an effective nuclear charge of 8. Then it says, which will experience the greater effective nuclear charge in the N equals 3 subshell? So the problem is, of course, it seems as though they are experiencing the exact same nuclear charge. However, that's because we're on 2 totally different energy levels here. Okay, so in argon, we're talking about the 3rd energy level. In krypton, we're now at the 4th energy level. So this is what those valence electrons are experiencing. So if we are focusing on the 3rd energy level electrons of krypton versus the 3rd energy level electrons of argon, krypton would have more attraction because it has a more positive nucleus. It has a higher actual nuclear charge. Okay, so the greater effective nuclear charge for the N equals 3 would be krypton because it has a higher actual nuclear charge. Alright, then it says which N equals 3 electrons will be closer to the nucleus. Well, again, argon only has a nucleus with a positive 18 charge. Krypton has a nucleus with a positive 36 charge. So again, the N equals 3 electrons, and now N equals 3 electrons just means the electrons in the 3rd energy level. So krypton again would have the closer electrons, and again it's because it has a higher actual nuclear charge. So its nucleus just actually is much more positive. Alright, so hopefully the calculating is not too difficult. I found for a lot of students the calculating is the easy part. It's questions like this that are the harder part for effective nuclear charge. Alright. So there we go. So next, maybe you should try this one. You're calculating the effective nuclear charge for Na and for Br. So pause the video and I'll assume you've done that, so let's look at them together. So for Na, remember, Z effective is our actual nuclear charge minus our screening constant. So for Na, it has an atomic number of 11. It is in group 1, so 1 of those electrons is a valence electron. So the other 10 are core electrons, so it has a 1 Z effective. 1. All right, for bromine, its actual nuclear charge is 35. It is in group 17, so 7 of those electrons are core electrons, so I will minus 28 from it. So those, 7 are valence electrons. So I'll minus 28 core electrons from it, and I get an effective nuclear charge of 7. Okay, and a lot of times you'll see the positives written next to it, but sometimes you'll just see the number. So I think what I did was I put the positives in my answer, just so that you're used to seeing that in case that's what you see on, like, you know, a test or something like that. All right, so hopefully you got both of those right. And to see here, I have my 1 positive and my 7 positive. All right, so now let's focus on the trends. So when we talk about the trend, we talk about what happens across the periodic table and down the periodic table. So the effective nuclear charge increases as we move across a row or period on the table. Although the number of core electrons stays the same as we move across, the actual nuclear charge increases. Okay, so as we go across, you can see sodium has a 1 positive, and then magnesium has a 2 positive, and so forth and so on. So as we move across, the number of core electrons stays the same. So our S value stays the same. See, it was 10 here, it's also 10 here. But our actual nuclear charge is increasing as we go across. So if you do a larger number minus the same number, you're going to keep getting larger answers. So effective nuclear charge increases across because the actual nuclear charge is getting stronger. So what happens when we go down? Well, going down a column, the effective nuclear charge increases slightly. If we actually calculate it, it's going to appear the same, as I'll show you right here, but we'll talk about what's going on. So actual nuclear charge is increasing as you move down a group. So, of course, we know our atomic number is increasing. But the larger electron cores are less able to screen the valence electrons. So in other words, what happens is when you have a small set of core electrons, they're pretty good at shielding the valence. But as the core electrons spread out, think about having not that many electrons, but in a larger area, they're not as good at shielding the valence electrons. So our simple Z-effective calculations make it seem like it stays the same. So like if I did F and Cl, F is going to be 7 positive and so is Cl. Because even though the actual nuclear charge has increased, so has the shielding effect. But technically, because Cl has a larger core group, they're not able to shield quite as much, so it just increases slightly. So for Z effective, it increases going across and increases slightly going down because those core electrons, as they get, as you get a bigger set of core electrons, they just can't shield as well. So the next term we're going to talk about is atomic radius or size. So atomic radius is the radius of an atom. In general, the atomic radius increases as you move down a group and decreases as you move across a period. The trends going across do not change as much when you move across the D and F sublevels. Okay, so when you're moving across the S and P, the trend going across is a larger change in radius or size than when you're moving across the D, which is the transition metals, or the F sublevels, which are your lanthanides and actinides. So when you get to those two areas, the change going across is very, very small. So the atomic radius increases going down a group because larger energy levels are added to each row. So like in row 1, we have 1 energy level. In row 2, we now have 2. In row 3, we now have a third one. So it just keeps getting larger. The atomic radius decreases going across a period because electrons are added to the same energy level. So it's not actually getting bigger. They're just in the same level. But protons are added to the nucleus, which means your Z effective increases, which pulls the electrons in closer. So a lot of people think that it should stay the same going across because you're just adding to the same energy level. But remember, because that Z effective, the nucleus is getting stronger, it can pull the electrons in closer. So that's what causes the decrease across a period. So, sample exercise. It says, arrange the following atoms in order of increasing size. So we have P, S, AS, and SE. So thankfully here, if you don't have a periodic table, I'll just throw these up real quick. So we have P, S, AS, and SE. Okay, so they're in a block of 4 right here. All right, so it says put them in order of increasing size. Well, for atomic size, it increases going down and decreases going across. So that means my smallest one, so we're putting in an order of increasing. So my smallest one is going to be S, because see, it's on the top and it's across decreasing. So then next would be P, and then I'm going to come down, but it decreases going across, so next would be SE, and then the largest would be AS. So another thing to know about atomic radius is the change is greater going down than across. Okay, so the fact that AS is larger than P outweighs the difference in AS and SE because they're just next to each other. There's just a small difference there. Okay, so our smallest one is S, our next one will be P, then I'm going to jump down to my bigger energy level, and between these two, SE would be smaller, and then AS, just like that. Alright, so hopefully you can follow the trends. A lot of people, they memorize the trends, but then when you get a question like this, they have a little bit of struggle with it. All right, so we have S, P, S, E, A, S. All right, so maybe pause it and try this one if you don't have a periodic table in front of you. This is the 7. We have B, E, M, G, and N, A. All right, so arrange these in order of increasing atomic radius. So pause it, try it, and I'll assume you've done that. All right, so remember, atomic radius increases going down and decreases going across. So we're putting it in increasing order, so that means I need to start with the smallest. So the smallest, of course, is BE, because remember, the change in radius is a greater amount as you go down. So immediately, if I need the smallest, I want to start at the top. So BE is the smallest. Now I'm going to come down here, so between these two, because it decreases going across, MG would be in the middle, and then NA would be the largest. And so that's all you have to do for those. Okay, so you just follow the trend, and hopefully you found this pretty easy. All right, so let's move on. All right, so the next thing we're going to talk about are ions. So an ion is just an atom with a charge. An atom has a charge when it gains or loses electrons. So an anion is a negative ion, which means it has gained electrons. And a cation is a positive ion, which means it has lost electrons. So I like to say the T in cation looks like a plus sign, so it's positive. All right, so an anion has gained electrons, a cation has lost electrons. So how do you know what charge something's going to have? Well, it's based on what group it's in on the periodic table. So you can tell the charge of an element based on which group it's in on the periodic table, except for transition metals. So every element in group 1 has a charge of positive 1. In group 2, positive 2. The transition metals, they all have positive charges, but it can be lots of different positives. Like iron can be positive 2 or positive 3. Copper can be positive 1 or positive 2. Vanadium can be positive 1, 2, 3, 4, or 5. So they have multiple charges, but they're all positive. Group 13, which has boron, has a positive 3. Group 14, I know this may be hard to see, this says plus or minus 4. And then group 15 has a negative 3, group 16 has a negative 2, group 17 has a negative 1, and then noble gases have a 0 charge. Because of course they have full outside energy level, and so they don't want to lose or gain. And so all they're doing is trying to get a full outside energy level. So for example, the group 1 elements, they have 1 valence electron, so it's easier to lose that 1 than try to gain 7 more to be stable. So when they lose that 1 electron, it has a positive 1 charge. Group 2, they have 2 valence electrons. So again, it's easier to lose 2 valence electrons than have to gain 6 more, so they become positive 2. Whereas like fluorine's group, this group 17, they have 7 valence electrons. So it's easier for them to just gain 1 more electron than try to lose 7, so they get a negative 1 charge. So the charges just occur to make an atom stable like a noble gas. And they're just like we are. They want to do the easiest possible way to get stable. And so that's where our positive and negative 4 comes into play. They have 4 valence electrons, so it's just as easy to lose 4 as it is to gain 4. So it just depends on what other element it's around. If it's around something that wants to gain electrons, then it will lose 4 and become positive 4. If it's around something that wants to lose electrons, it will gain those 4 and then have a negative 4 charge. So the positive or negative 4 just means we would need to know what element it's bonding to. So the next trend is ionization energy. So ionization energy is the energy needed to remove an electron from an atom. In general, ionization energy decreases as you move down a group and increases as you move across a period. So ionization energy is going to decrease going down and increase going across. So it's actually the exact opposite of atomic radius. So why does this happen? Well, ionization energy decreases as you move down a group because larger energy levels are added, which are farther from the nucleus. Since the electrons are far from the nucleus, it takes less energy to remove one. Okay, so ionization energy is the energy needed to remove an electron. The farther we are from the nucleus, the easier it is to remove. So the amount of energy we need to remove it decreases. So again, it's based on those larger energy levels. You'll notice a pattern here. Ionization energy increases as you move across a period, Because the nucleus gets stronger, which means our Z effective increases, so it takes more energy to remove an electron. So as we go across, we're staying the same distance from the nucleus. We're just adding to the same energy level. But the nucleus is getting stronger, and so that's what requires a higher energy as we go across. So again, just like atomic radius, the down trend is based on energy levels, and the across trend is based on your Z effective. You'll find that as a pattern for these. So let's look at our next one. It says, arrange the following atoms in order of increasing first ionization energy. Oh gosh, and of course they're like all over the place. So here, let me just throw a quick periodic table up here in case you're not looking at one, and I'll put them where they are. All right, so we have AR kind of about right here, and we have NE above that. We have P kind of over here. Let's see, we have Na over here. And what am I missing? K. We have K right here. Alright, so Na is at our third energy level, K is at our fourth energy level, just to kind of keep you up with where we are. N is at the second energy level, and P and AR are both at our third energy level, because I know it's kind of hard to follow across. So see, these are all on the third, this is on the second, K is on the fourth. So ionization energy, as you go down, it decreases. As you go across, it increases. And like I said, y'all, I always focus on the down first before I focus on what's happening across. Okay, so we want to arrange them in order of increasing first ionization energy. So we're going to go from low to high. All right, well, it decreases going down. So the furthest down on the periodic table is K. So that's going to be my lowest. Alright, next I'm going to move up to the third energy level. So now I've got to focus on Na, P, and AR. Well, it increases going across, so that means Na would have the next lowest, then P, then AR, and then remember, it decreases going down, so since Ne is the highest on the periodic table, it would have the highest ionization energy out of these right here. Okay, so again, y'all, if you're given elements in multiple periods and multiple groups, focus on the rows first. So like notice I didn't look at anything but row 4 first. Then I moved to row 3, then I moved to row 2. Focus on the rows first and then look across. Okay, so focus on up and down first and then look across. That's the easiest way to do it. Right? So maybe pause it and try these next two real quick. So it says which has lowest first ionization energy between B, AL, C, or SI, and then which has the highest first ionization energy. So again, if you don't have a periodic table, the setup of these are B, C, AL, SI. Alright, so that's the setup. Alright, so I'm going to assume that you paused the video and tried it, so let's look at it together. So ionization energy decreases going down and increases going across. Alright, so if I'm looking for the lowest, I'm going to discount this row, okay, because it decreases going down. So these are lower, and then between these two, it increases going across, so I can see that AL has the lowest. Alright, see that's the problem is once y'all try to focus on all 4 of them, okay, like I said, just focus on the down first, and then narrow it down for the across. Alright, then it says which has the highest first ionization energy. Well, it decreases going down, so I'm going to discount this row. So now I'm just between boron and carbon. Well, it increases going across, so it would be carbon. Alright, so once you can just take a minute to focus, draw it out if you need to. These aren't really that bad, but a lot of people struggle with these. Alright, so notice that the values for a given element increase as successive electrons are removed. So what I have right here are different ionization energy. So first ionization energy removes 1 electron. The second ionization energy is what we then have to put forth to remove a second electron. Third ionization energy, we're now trying to remove a third electron, so forth and so on. This trend exists because each extra electron is being removed from an increasingly positive ion. Okay, so here's our first ionization energies. Here's our second. So you can see they're always greater. Here's our third. They're always greater. And our fourth. Because every time you're removing another electron, that is going to take more and more energy to pull it away from that positive nucleus. So you'll see that there's a sharp increase in the ionization energy that occurs when an inner shell electron is removed. This is the reason that only valence electrons are involved in bonding. So when you see a very sharp increase in the ionization energy, that's when you've reached a core electron. Okay, so for example, if you look here, boron has 3 valence electrons. So the first ionization energy is 800, the second one's about 2,000, the third one's about 3,000, and then all of a sudden the fourth one jumps to 25,000. Okay, so you're going to see an increase across, but all of a sudden we get this huge increase. That's because it only has 3 valence electrons. So once we try to pull the fourth valence electron, that has now become a core electron instead. And so that's why you see that gigantic increase. Okay, the same thing happens, like for example, magnesium has 2 valence electrons. So the first ionization energy is only about 700, the second is only about 1,000, and then all of a sudden it jumps to almost 8,000. That's because you've removed the 2 valence, and so now you're trying to pull a core electron. Alright, so it says based on their locations on the periodic table, does sodium, calcium, or sulfur have the highest second ionization energy? Okay, so let's look at where they are real quick, in case you don't have a periodic table. Alright, so over here we have sodium, which is about right here. Alright, we have calcium, which is right under sodium but over 1, and then we have sulfur, which is kind of over here. So really it's based on valence electrons. Sodium has 1 valence electron, calcium has 2 valence electrons, and sulfur has 6. So who would have the highest second ionization energy? Well, sodium kind of wants to lose its valence electron anyway, but once it loses that 1, now you're picking on the core electrons. Okay, so sodium would be the one that would have the highest second ionization energy. Because calcium, it has 2 valence. So it's not a big deal to remove the first one. It's not really a big deal to remove the second one. So it wouldn't have a very high one. It actually wants to lose both those valence electrons anyway. Sulfur, it has 6 valence electrons. So really it's trying to gain 2. But you know, if we took 2 from it, we still haven't reached the core electrons yet. And that's when you see that spike in ionization energy. Alright, so maybe pause it and try this one. And so it says, which will have the greater third ionization energy, calcium or sulfur? And so in case you don't have a periodic table, let me just kind of give you the positions again. Calcium is here and sulfur is over here. Calcium has 2 valence, sulfur has 6. So I'm going to assume you paused it and tried it. So we're looking at third ionization energy. Well, calcium only has 2 valence electrons. So once we remove those 2, we are reaching core electrons. So it's going to be calcium. Sulfur, on the other hand, again, it has 6. So even though really it wants to gain 2 more electrons, it's still not a big deal if we try to remove 3 because it has 6 valence. So we haven't actually reached the core electrons yet. So hopefully you got that one right. So really when it's focusing on multiple ionization energies, that is when you start to notice that huge jump in the value for the ionization energy. Alright, so those are our first couple of trends. For the rest of them, just watch the part 2 of this lesson video.